Thank you, ladies and gentlemen. I am Nikolaos Koukoudakis, and today we will talk about learning from the data, how to treat correlated data sets. Now, our main problem for today is this least squares problem. Here we have the X, which is the design matrix, data matrix, as we also call it, which is a n by d plus 1 matrix. And we also have the regression parameter, which is what we intend to calculate, which is a vector with dimensions 1 and d plus 1. Now, we also include a small noise, epsilon, which we use to check the system's stability. So if one method succeeds with epsilon, then that means we can trust this method for other real-time real dataset problems. Let's head on to the state of the art. We have two different paths which we can follow. The first path is the direct method, the minimum norm solution. In this method, we intend to minimize this norm, y minus x beta all squared, and this is a really direct method. Now, for the second path, we use something that's called regularization. There are many techniques to regularize datasets, and one of them is Tikhonov. The Tikhonov regularization uses the parameter lambda, and the LPLQ regularization uses many parameters. However, that includes that we solve a wholly different problem, and that complicates the situation. So our objective is to study the data matrix and study all of its properties so that we can later decide whether regularization is required or not. Now, the first method we initially talk about is the minimum norm solution. We will call it MNS from now on. We will try to minimize this norm, and after many calculations and many applications of linear algebra properties, we come up with this formula on our screens. Using the SVD decomposition, we can calculate this sum, which is more stable than the previous formula. Next, we have the Tikhonov regularization, which is also known as regression. Now we introduce the parameter lambda, which complicates the situation, complicates our problem. Using linear algebra properties, we come up with a very useful formula, and using the SVD decomposition, we simplify it and make it more stable. There are many ways to, this calculates the regression parameter for a given lambda. However, we should compute lambda so that we get the optimal value of beta. There are many ways to compute and to find the optimal value of lambda, and we use the Brent's algorithm. That is because we use the Julia programming language and the respective package for regularization tools. Finally, we have the LPLQ regularization, which does not use one, but three parameters, P, M, and Q. Now, P and Q must be between 0 and 2, and M is respective to lambda, as we saw it on the previous method. However, here we have three parameters. We need to be very careful on how to choose them, because we need time, and the time that we will use to find those parameters values can be very valuable. Now let's head on to the construction of the design matrix, which we haven't talked about so far. Let's talk about it now. We have the first method out of 4 on total, which is the column correlated covariates. Now we use a diagonal matrix as a covariance matrix and calculate the values using the normal distribution. And then we can of course compute the correlation coefficient using this formula on the screen. Additionally, we also have a second method for constructing the data matrix. That's called the element correlated covariates, and we start with a square matrix, which has the property that is shown on the screen, and we use that matrix to calculate x. This is the algorithm for the already described method. First, we calculate the values of sigma, and then according to the correlation coefficient R, and then we calculate the values of x using probabilistic methods. Then we have the toy model. Now, this is a different type of construction model, which is simplistic, and that makes it more easy to work with. This simplicity offers us the opportunity to evaluate our conclusions easier. We use this formula to calculate the values of the design matrix, and each column of x is correlated to one another with the correlation coefficient of R squared. Last but not least, we use the spiked covariance model. This is a very interesting model as we construct the covariance matrix as shown on the screen. However, this is a spiked model, so as we see in this example, sigma has 3 eigenvalues. 3 are the 2 of them are just 1, and the other one, lambda 1, comes out as a spike, and that is the evaluation of the name. This is exactly how we construct the data matrix. Now, it's time to examine and it's time to implement what we have already discussed. We use the relative mean square error and in order to evaluate which method is more accurate. The algorithm that we use is the following. We calculate first the beta, the regression parameter, which consists of randomly generated numbers from the normal distribution, and then we calculate the y. Now, the beta that we calculated is the exact regression parameter that we want to find. And now we create 100 training sets. For each one of them, we calculate beta, 3 vectors, each for each method, MNS, Tikhonov, and LPLQ. We calculate the relative mean square error, and then we find out which method is the best for each occasion. Let's observe some of the results, which are very intriguing. For starters, in CCC, we can observe that MNS can yield satisfactory results for small r, for example 0.5 or 0.9, sigma squared plays small role in this equation. However, as the columns become more highly correlated, MNS is no longer satisfactory, and we need regularization techniques. That can be evaluated and confirmed by the next with the next charts, which we have tested in many methods. For example, we observed ECC, now element covariate, and we always test different and larger potentially dimensions for the data matrix. Here in the toy model, we can also validate that for bigger matrices and larger number of columns, we can see that regularization is no longer needed. For example, in this overdetermined case, we can see that MNS is unsatisfactory, unacceptable for 0.999. However, when we observe the 64 by 1000 data matrix, the MNS is very satisfactory, and any regularization is proven is not proven required. That can also be said about the spikes model for various dimensions, because the MNS proves satisfactory results as the number of columns keeps increasing. We have also confirmed that for the Tikhonov regularization, as we decrease the value of the optimal lambda, the lambda best, we get similar errors as D increases. So for a larger number of columns, we get similar errors. However, if the columns are if the columns are less, which means an overdetermined case, or similar numbers, similar number of columns and rows, then lambda best is clearer. This is a simple diagram of our research, which shows exactly what we have concluded. So in the highly correlated matrices, which means the R is approximately 1, we use the regularization techniques only if the data is not the data matrix is not highly dimensional. However, we can use the MNS, and it is very satisfactory if the data is high dimensional, or if the data is not highly correlated, which means that R is less or equal than 0.9. That means that X is well conditioned. Thank you for your time and your attention.
Yes. Thank you very much for your presentation, your report. Maybe my question will be strange. My question is the following. At the beginning of your presentation, the state of the art section, you talk about 2 different options. Yes?
Yes.
My question is, can we use your result, and can we combine benefits of different methods to assure, to provide any more high-level technical characteristics? My question is as a question of engineering to mathematics. Okay? Do you understand my question? Usually we talk if you have 2 options or more options, depending on value of parameters, we can select choice one or other methods, one or other procedure techniques. Yes, but usually there is adaptation approach when we depending on value of parameters can in real time apply both methods or few methods. And so my question is, can you results help to answer for my question or to help find more efficient decision?
Yes, I
In
think.
point of view of practice.
Yes, I think that we can always adjust many things in the theoretical background, in our work in mathematical background, and that could mean that we increase the efficiency for our algorithms, and then choose the best method for our approach.
Yes, but I say about possibility apply special solution device to make decision in real time which methods will be better for depending on value of parameters.
I don't think I followed.
Sorry?
Sorry, I don't think I followed.
I think we can discuss this point because collaboration is this one. The important thing is for any real data set, when you want to solve it, can you solve it directly or you need to apply regularization? And this is really very important because in many approaches, most of them they say, oh, the matrix is not square, regularization is needed. Since we have error or since we have noise, apply regularization. But regularization is not so simple because you not make the problem. You need to think about the value of the regularization parameter, how to apply one parameter to its very complicated. The appropriate choice and with the values of methods of how to choose the regularization parameter. So what we try to do is maybe according from the data. Sometimes you can solve it directly, for example, with the meaningful norm solution, they behave well, and you avoid regularization. So for each data set, study the problem.
I see. Thank you. And now I better understand. Yes, but there is other side. If you talk about data set,
Yes.
what I mean, for example, now we have a special request for pattern where we apply two different techniques to build the same, but by using different technique of building two channels, in point of view regarding all tolerance systems based on narrowness and so on. And in this case, there is very interesting point how we can get different set of data sets or any other techniques which would help to get the same decision, but using different techniques or different parameters of techniques. In this case, we have less value of the risk of common cost failure. I talk about this problem in point of view how get to version is minimal crossing or potential reason for failure. And
Okay, I suggest to continue the discussion for a break. We thank again the speakers, all the speakers.